Formats for encoding data. Programs usually work with data in at least two different representations. In memory, data is kept in objects, structs, lists, arrays, hash tables, trees, and so on. These data structures are optimized for efficient access and manipulation by the CPU, typically using pointers. When you want to write data to a file or send it over the network, you have to encode it as some kind of self-contained sequence of bytes, for example, a JSON document. Since a pointer wouldn't make sense to any other process, this with the exception of some special cases, such as certain memory-mapped files or when operating directly on compressed data as described in column compression on page 97. Roman 2. Note that encoding has nothing to do with encryption. We don't discuss encryption in this book. Sequence of bytes representation looks quite different from the data structures that are normally used in memory. Thus, we need some kind of translation between the two representations. The translation from the in-memory representation to a byte sequence is called encoding, also known as serialization or marshalling, and the reverse is called decoding, parsing, deserialization. Unmarshalling. Roman 2 serialization is unfortunately also used in the context of transactions, see Chapter 7, with a completely different meaning. To avoid overloading the word, we'll stick with encoding in this book, even though serialization is perhaps a more common term. As this is such a common problem, there are a myriad different libraries and encoding formats to choose from. Let's do a brief overview. Language-specific formats. Many programming languages come with built-in support for encoding in-memory objects into byte sequences. For example, Java has Java.io.serializable 1, Ruby has Marshall 2, Python has Pickle 3, and so on. Many third-party libraries also exist, such as Cryo for Java 4. These encoding libraries are very convenient because they allow in-memory objects to be saved and restored with minimal additional code. However, they also have a number of deep problems. The encoding is often tied to a particular programming language, and reading the data in another language is very difficult. If you store or transmit data in such an encoding, you are committing yourself to your current programming language for potentially a very long time, and precluding integrating your systems with those of other organizations, which may use different languages. In order to restore data in the same object types, the decoding process needs to be able to instantiate arbitrary classes. This is frequently a source of security problems. If an attacker can get your application to decode an arbitrary byte sequence, they can instantiate arbitrary classes, which in turn often allows them to do terrible things such as remotely executing arbitrary code. Versioning data is often an afterthought in these libraries, as they are intended for quick and easy encoding of data. They often neglect the inconvenient problems of forward and backward compatibility. Efficiency, CPU time taken to encode or decode, and the size of the encoded structure is also often an afterthought. For example, Java's built-in serialization is notorious for its bad performance and bloated encoding. For these reasons, it's generally a bad idea to use your language's built-in encoding for anything other than very transient purposes. JSON, XML, and binary variants. Moving to standardized encodings that can be written and read by many programming languages, JSON and XML are the obvious contenders. They are widely known, widely supported, and almost as widely disliked. XML is often criticized for being too verbose and unnecessarily complicated. JSON popularity is mainly due to its built-in support in web browsers, by virtue of being a subset of JavaScript and simplicity relative to XML. CSV is another popular language-independent format, albeit less powerful. JSON, XML, and CSV are textual formats, and thus somewhat human-readable, although the syntax is a popular topic of debate. Besides the superficial syntactic issues, they also have some subtle problems. There is a lot of ambiguity around the encoding of numbers. In XML and CSV, you cannot distinguish between a number and a string that happens to consist of digits except by referring to an external schema. JSON distinguishes strings and numbers, but it doesn't distinguish integers and floating-point numbers, and it doesn't specify a precision. This is a problem when dealing with large numbers. For example, integers greater than 253 cannot be exactly represented in an IEEE 754 double precision floating-point number, so such numbers become inaccurate when parsed in a language that uses floating-point numbers such as JavaScript. An example of numbers larger than 253 occurs on Twitter, which uses a 64-bit number to identify each tweet. The JSON returned by Twitter's API includes tweet ID twice, once as a JSON number and once as a decimal string. to work around the fact that the numbers are not correctly parsed by JavaScript applications. JSON and XML have good support for Unicode character strings, i.e. human-readable text, but they don't support binary string sequences of bytes without a character encoding. Binary strings are a useful feature, so people get around this limitation by encoding the binary data as text using base 64. The schema is then used to indicate that the value should be interpreted as base 64 encoded. This works, but it's somewhat hacky and increases the data size by 33%. There is optional schema support for both XML and JSON. These schema languages are quite powerful, and thus quite complicated to learn and implement. Use of XML schemas is fairly widespread, but many JSON-based tools don't bother using schemas, since the correct interpretation of data such as numbers and binary strings depends on information in the schema. Applications that don't use XML/JSON schemas need to potentially hardcode the appropriate encoding/decoding logic instead. CSV does not have any schema, so it is up to the application to define the meaning of each row and column. If an application change adds a new row or column, you have to handle that change manually. CSV is also a quite vague format. What happens if a value contains a comma or a new line character? Although its escaping rules have been formally specified, not all parsers implement them correctly. Despite these flaws, JSON, XML, and CSV are good enough for many purposes. It's likely that they will remain popular, especially as data interchange formats, i.e. for sending data from one organization to another. In these situations, as long as people agree on what the format is, it often doesn't matter how pretty or efficient the format is. The difficulty of getting different organizations to agree on anything outweighs most other concerns. For data that is used only internally within your organization, there is less pressure to use a lowest common denominator encoding format. For example, you could choose a format that is more compact or faster to parse. For a small dataset, the gains are negligible, but once you get into the terabytes, the choice of data format can have a big impact. JSON is less verbose than XML, but both still use a lot of space compared to binary formats. This observation led to the development of a profusion of binary encodings for JSON message pack, BSON, BJSON, OBSON, BISON, and SMILE, to name a few, and for XML, WBXML, and FAST and FAUCET, for example. These formats have been adopted in various niches, but none of them are as widely adopted as the textual versions of JSON and XML. Some of these formats extend the set of data types, for example distinguishing integers and floating-point numbers, or adding support for binary strings, but otherwise they keep the JSON/XML data model unchanged. In particular, since they don't prescribe a schema, they need to include all the object field names within the encoded data. That is, in a binary encoding of the JSON document in example 4-1, they will need to include the string's username, favorite number, and interest somewhere. Example 4-1, example record, which we will encode in several binary formats in this chapter. Let's look at an example of message pack, a binary encoding for JSON. Figure 4-1 shows the byte sequence that you get if you encode the JSON document in example 4-1 with message pack. The first few bytes are as follows. The first byte, 0x83, indicates that what follows is an object. Top 4 bits equals 0x80 with 3 fields. Bottom 4 bits equals 0x03. In case you're wondering what happens if an object has more than 15 fields, so that the number of fields doesn't fit in 4 bits, it then gets a different type indicator, and the number of fields is encoded in 2 or 4 bytes. 2. The second byte, 0za8, indicates that what follows is a string. Top 4 bits equals 0za0, that is 8 bytes long. Bottom 4 bits equals 0x08. The next 8 bytes are the field name username in ASCII. Since the length was indicated previously, there's no need for any marker to tell us where the string ends or any escaping. The next 7 bytes encode the 6-letter string value Martin with a prefix 0za6, and so on. The binary encoding is 66 bytes long, which is only a little less than the 81 bytes taken by the textual JSON encoding with whitespace removed. All the binary encodings of JSON are similar in this regard. It's not clear whether such a small space reduction and perhaps a speed-up in parsing is worth the loss of human readability. In the following sections we will see how we can do much better and encode the same record in just 32 bytes. Figure 4-1. Example record. Example 4-1 encoded using message pack. Thrift and Protocol Buffers. Apache Thrift and Protocol Buffers Protobuf are binary encoding libraries that are based on the same principle. Protocol Buffers was originally developed at Google, Thrift was originally developed at Facebook, and both were made open source in 2007-08. Both Thrift and Protocol Buffers require a schema for any data that is encoded. To encode the data in example 4-1 in Thrift, you would describe the schema in the Thrift interface definition language IDL like this. Actually, it has three: binary protocol, compact protocol, and dense protocol, although dense protocol is only supported by the C++ implementation, so it doesn't count as cross-language. Besides those, it also has two different JSON-based encoding formats. What fun! The equivalent schema definition for protocol buffers looks very similar. Thrift and Protocol Buffers each come with a code generation tool that takes a schema definition like the ones shown here and produces classes that implement the schema in various programming languages. Your application code can call this generated code to encode or decode records of the schema. What does data encoded with this schema look like? Confusingly, Thrift has two different binary encoding formats, Roman 3 called binary protocol and compact protocol, respectively. Let's look at binary protocol first. Encoding example 4-1 in that format takes 59 bytes, as shown in figure 4-2. Figure 4-2. Example record encoded using Thrift's binary protocol. Figure 4-3. Example record encoded using Thrift's compact protocol. Figure 4-4. Example record encoded using protocol buffers. Similarly to figure 4-1, each field has a type annotation to indicate whether it is a string, integer, list, etc. and, where required, a length indication length of a string, number of items in a list. The strings that appear in the data Martin, daydreaming, hacking are also encoded as ASCII or rather, UTF-8, similar to before. The big difference compared to figure 4-1 is that there are no field names, username, favorite number, interests. Instead, the encoded data contains field tags, which are numbers 1, 2, and 3. Those are the numbers that appear in the schema definition. Field tags are like aliases for fields. They are a compact way of saying what field we're talking about, without having to spell out the field name. The Thrift compact protocol encoding is semantically equivalent to binary protocol, but as you can see in figure 4-3, it packs the same information into only 34 bytes. It does this by packing the field type and tag number into a single byte, and by using variable length integers. Rather than using a full 8 bytes for the number 1337, it is encoded in 2 bytes, with the top bit of each byte used to indicate whether there are still more bytes to come. This means numbers between 64 and 63 are encoded in 1 byte. Numbers between 8192 and 8191 are encoded in 2 bytes, etc. Bigger numbers use more bytes. Finally, protocol buffers, which has only one binary encoding format, encodes the same data as shown in figure 4-4. It does the bit packing slightly differently, but is otherwise very similar to Thrift's compact protocol. Protocol buffers fits the same record in 33 bytes. One detail to note: in the schemas shown earlier, each field was marked either required or optional, but this makes no difference to how the field is encoded. Nothing in the binary data indicate whether a field was required. The difference is simply that required enables a runtime check that fails if the field is not set, which can be useful for catching bugs. We said previously that schemas inevitably need to change over time. We call this schema evolution. How do Thrift and Protocol Buffers handle schema changes while keeping backward and forward compatibility? As you can see from the examples, an encoded record is just the concatenation of its encoded fields. Each field is identified by its tag number, the numbers 1, 2, 3 in the sample schemas, and annotated with a data type, for example string or integer. If a field value is not set, it is simply omitted from the encoded record. From this you can see that field tags are critical to the meaning of the encoded data. You can change the name of a field in the schema, since the encoded data never refers to field names, but you cannot change a field's tag, since that would make all existing encoded data invalid. You can add new fields to the schema, provided that you give each field a new tag number. If old code which doesn't know about the new tag numbers you added tries to read data written by new code, including a new field with a tag number it doesn't recognize, it can simply ignore that field. The data type annotation allows the parser to determine how many bytes it needs to skip. This maintains forward compatibility. Old code can read records that were written by new code. What about backward compatibility? As long as each field has a unique tag number, new code can always read old data, because the tag numbers still have the same meaning. The only detail is that if you add a new field, you cannot make it required. If you were to add a field and to make it required, the check would fail if new code read data written by old code, because the old code will not have written the new field that you added. Therefore, to maintain backward compatibility, every field you add after the initial deployment of the schema must be optional or have a default value. Removing a field is just like adding a field, with backward and forward compatibility concerns reversed. That means you can only remove a field that is optional. A required field can never be removed, and you can never use the same tag number again because you may still have data written somewhere that includes the old tag number, and that field must be ignored by new code. What about changing the data type of a field? That may be possible. Check the documentation for details, but there is a risk that values will lose precision or get truncated. For example, say you change a 32-bit integer into a 64-bit integer. New code can easily read data written by old code because the parser can fill in any missing bits with zeros. However, if old code reads data written by new code, the old code is still using a 32-bit variable to hold the value. If the decoded 64-bit value won't fit in 32 bits, it will be truncated. A curious detail of protocol buffers is that it does not have a list or array data type, but instead has a repeated marker for fields, which is a third option alongside required and optional. As you can see in figure 4-4, the encoding of a repeated field is just what it says on the tin. The same field tag simply appears multiple times in the record. This has the nice effect that it's okay to change an optional single-valued field into a repeated multi-valued field. New code reading old data sees a list with 0 or 1 elements depending on whether the field was present. Old code reading new data sees only the last element of the list. Thrift has a dedicated list data type, which is parameterized with the data type of the list elements. This does not allow the same evolution from single value to multi-valued as protocol buffers does, but it has the advantage of supporting nested lists.